All right, so we're going to go over a couple of things here, kind of just review of the stuff affecting both gravitational potential energy as well as kinetic energy, because those are obviously the two big parts of mechanical energy, which is what we've been dealing with. And next week, we're going to be moving on to the law of conservation of mechanical energy. That's the roller coaster stuff you would have done in Science 10. Okay, so we'll be moving on to that, talking about power, okay, next week, and then doing our unit exam review, probably on like Thursday or something like that, right? So we'll be doing that, yeah, Wednesday or Thursday, okay, that we'll do the unit exam review. So it's coming up, okay, because basically everything else in the unit is new, and power, you just have to know what it is. You don't have to solve any problems for it. So okay, we're done kind of the tricky stuff that you haven't seen before. Okay. All right, so in order to have gravitational potential energy, okay, a few things have to be present. Gravity. Okay, you have to have gravity to have gravitational potential energy. So if I was out in like interstellar space where there was, essentially no gravitational body near enough to exert any considerable force of gravity on me, I would have no gravitational potential energy because I'm not accelerating, or nor do I have the potential to accelerate towards anything. Okay, but as long as I'm near some gravitational body, then I will have gravitational potential energy. All right, the other thing is I have to be at a certain height away from the surface or center of that body. Okay, that's where the formula, okay, comes from. And we talked about this the other day, that potential energy is equal to the change, or work is equal to the change in potential energy, and that's force times distance. For gravitational potential energy, the force we work against is gravity, which we calculate by multiplying m times g, and the distance over which that force acts is height. Height is a vertical distance. All right, so that's where that formula comes from. Okay, so as we said, we have to have gravity. We have to have some distance away from the surface that we could fall to, and there has to be something there. There's no mass. There's no ability to do anything. Okay, so we have to have some mass as well. All right, things we have to understand about this formula. Okay, if I have two objects, one is a tennis ball and the other is a grand piano, and they're both hanging over the edge of a building, which one do I want to stand under? Well, it depends where you're thinking your life is going, I suppose. Probably not the piano, okay? I would probably want to stand underneath the tennis ball, because if one of them or both of them were to fall off the building, I'd much rather get hit by the tennis ball. Okay, why? Because it has less mass. If it has less mass, when it gets down to the ground, it's going to have less energy and thus less ability to do work on me and change my shape in an undesirable way. Okay, everyone kind of follow me on that. Even in the perfect physical world, where if they both accelerated all the way down and were going the same speed when they hit me, okay, obviously in the real world, the tennis ball wouldn't be going as fast as the piano, okay, but in the perfect physical world, they'd be going the same speed. I'd still rather get hit by the tennis ball. Okay, it has less mass. Right. Everyone kind of follow me there. Okay, that's why, like, if you've ever gone like downtown in Calgary where they're doing construction, okay, they always have the covers over the sidewalks. Okay, that's so that any little piece of debris that might fall off of the building can't hit anybody. All right. I mean, even something small, if it were to, fall down, it could hurt you pretty badly. Okay. There's like this whole idea that if you dropped a penny off of the Empire State Building, it would like drive a hole through your head if it hit you, which is completely false, by the way. Okay. The penny would tumble and actually not be going that fast. All right. But if something heavier like a hammer were to fall off of the building, that could pose a pretty major safety issue to people underneath. So they have to cover up the sidewalks because of that. Okay, so we've talked about that. Okay, so if we're looking at like a ride like the Space Shot, okay, at West Edmonton Mall, how many people have been on that before? Okay, so after the end of May, everyone will be able to put up their hands, okay, because everyone's going to ride it when we go there. Okay, we're still working on a date, by the way, but we'll have that to you soon. All right, so if I'm looking at this ride and the ride is at its highest point, in this case, not the Space Shot, 48 meters above ground level, I can calculate its potential energy. All right, so the ride is 500 kilograms, so they tell us the mass, they tell us the height, and we assume this ride is on Earth where gravity is 9.81. So we can calculate its potential energy very easily, just m times g times h, 500 times 9.81 times 48 meters. whoop, not 9.1, 9.8. All right, so it would have 235,440 joules worth of potential energy, which is why it's so much fun to be on one. Because all that potential energy, when the ride falls, is going to turn into kinetic energy, right? And so you'll be going really, really fast at the bottom. Now, obviously in the real world, not all of it gets turned into kinetic energy. There's air resistance. The ride doesn't actually let you free fall, okay? There is resistance in there. Okay? When you do the calculations for the space shot, you'll find that the acceleration of the space shot, even though it feels like you're free falling, is actually like just over half of the acceleration due to gravity. It isn't like you're free falling, okay? If you've ever like bungee jumped, that's way different than the space shot is. Way, way different. Okay? Or jumped off like the 10-meter diving platform. Okay, it feels a lot different to jump off the high diving board than it does on the space shot. Okay, the thing about the space shot that makes it feel like you're free fall is the fact that you're shot upwards first. Okay, they don't just like slowly drag you to the top and then drop you. They shoot you to the top. Okay, and then you stop suddenly at the top, and that gives you that feeling of that I'm going to fall now, okay? Which is of course what they're looking for. Okay? So if you've ridden it, you've seen your pictures, right? Like when you get to the top, if you have long hair, your hair is like straight up above you. Okay, that's Newton's first law. They stopped you. Everything else kept going. Okay? We actually had a kid who got in really big trouble one time on this trip because he put a penny in his hand. Okay, and they shot him, the ride shot upwards, and in the picture there's a penny floating right in front of his face because the ride stopped and the penny flew up off of his hand. Okay, and when they saw that on the picture, they hauled him away and were like, oh look, he made a mistake, you know, don't put him in jail. But it's a big deal if that penny had gotten into the machinery of the ride, right? Like that, they make you take your shoes off, if you know, and things like that, because they don't want anything to get into the machinery of the ride. So it was a pretty stupid thing to do, even though the picture looked really cool. Okay, it was a pretty stupid thing to do. What's that? You know what? We never got to that point. There was too much begging and pleading to let him come home with us. Yeah. All right. So I want you guys to write down this example. We're going to try it together. Okay, so I got this toy car set up on this track on a tabletop. Okay, we want to find out what the gravitational potential energy of the car is if its mass is, okay, 0.025 kilograms or 25 grams relative to the floor. Right? So the importance of this question is a reference point. Okay? Most of the time when we're talking about potential energy, our reference point is ground level because that makes the most sense. But they could have also asked this question, okay, what is the gravitational potential energy relative to the bottom of the track? Right? Because really that would be the place where it would stop accelerating until, of course, it went off the end of the table. So reference points are important. Most of the time, if they don't mention otherwise, the reference point is the ground. Okay? All right, so in this question, if I want to calculate the potential energy of the car relative to the floor or the ground, which height am I using? The 0.950 or the 2.15? Yeah, I want to use the 2.15 because that's relative to the floor. The car is here, 2.15 meters above the floor, right? This one is just from the top of the table to the floor. Okay, so EP is just going to be m times g times h, 0.025 times 9.81 times 2.15 meters. All right, so I've got 0.527 joules. Right? So not very much energy because it's not a very big car. All right, calculate the change in gravitational potential energy of the car when it arrives at the bottom of the hill. All right, so this is my initial potential energy because it's the top of the hill. Okay, I want to find the change. Okay, then I'm going to do what we've been doing basically all week. It's going to be m times g times hf minus m times g times hi. I just already have this number. Okay, so my change in potential energy will be 0.025 times 9.81 times the height of the table here for my final 0.95. All right, so the change is negative 0.29 joules. Why is it negative? Did the car gain it or lose it? Yeah. Right, the height will be less, so I'm losing potential energy. Am I losing mechanical energy? No. Okay, all that's happening is the potential is turning into kinetic. Okay, that's law of conservation of energy. Unless there's some friction. Okay, if there was friction, then there would be some energy lost to friction. It would be sound and heat and other things. Okay, and we already know kind of how to deal with that stuff. All right, I want you guys to try question number 1 here. Okay, it's about a pile driver, not the wrestling move. Okay, but the wrestling move, oddly enough, looks just like what a pile driver does. It takes a really big mass and drops it, okay, onto something else, a piling in this case. Okay, so when they're building like skyscrapers and stuff like that, they want to put pilings or footings into the ground below the frost line, so that when the ground freezes, it doesn't heave and push the building around. Okay, so we put these pilings in the ground. Okay, so basically they're a big concrete pillar, and the pile driver is just a big mass that they pull up on a crane and then drop, and it slams down onto the piling, driving it into the ground. Pile driver. Okay, I know where it comes from, but the wrestling move does look a lot like it, okay, where you turn a guy upside down and jump on his head. Yeah. All right, so if we want to calculate the potential energy of the pile driver when it's at its highest point, okay, then we want to take, obviously, its mass, 550. We're going to multiply by 9.81 and the height above the ground, because the question does specifically refer to ground level as our reference point. Okay, so we're going to take EP equals m times g times h. Okay, 550 kilograms times 9.81 times 12.5 meters. All right. Well, it's a given. It's one of my givens, right? It's the initial height. Okay, that sort of makes sense. All right, so when we do that, we're going to have, so 550 okay, times 9.81 times 12.5. Okay, so our potential energy at that point, we only have 3 significant figures there, okay, is going to be 6.74 times 10 to the 4 joules. All right, the second thing they ask at its lowest point. Well, its lowest point is sitting on top of the piling, where it's still how far above ground level? 2.3 meters. Okay, so we've got to find, so this is essentially, we found the initial potential. Now we're looking for the final potential. So again, 550 times 9.81 times 2.3 meters. And so when we do that, all right, so we have 12,409, so 1.24 times 10 to the 4 there. Weird. Okay, that's 10 to the 4 joules. All right, so we've got that. Now I know initial and final. Okay, can I now find the change? Right, it's just like we've been doing all along with work energy theorem. I'm just going to subtract final minus initial. I'm going to get a negative number again because it's going to lose potential energy. It's turning into kinetic. That kinetic is going to do what when it hits the pile driver? If I have energy, I can do this. Work. Yeah, it's going to do work. It's going to drive the piling into the ground, okay, against the force of friction, okay, the resistance of the earth as it drives it into the ground. All right. Let's have you guys try 2 and 3 here now. We've done lots like that. Actually, we're out of time because it's 9:28. So next week, okay, we're going to talk about, we'll talk quickly about kinetic, and then we'll talk about conservation energy, which should be a review for everybody.